In a modern enterprise environment, retiring a single legacy application is a high-stakes operation. A modern network is dense with undocumented connections. Missing even one upstream dependency during a shutdown sequence can trigger a cascading failure, knocking active production systems offline. Engineering teams have historically relied on manual codebase analysis to map these connections. In complex, sprawling microservice architectures, this process is slow and highly vulnerable to human error. Replacing that manual effort by granting an unconstrained large language model omnipotent access to the enterprise network presents an unacceptable security risk. The LoRa decommissioning suite provides a secure alternative. Built on the Google Anti-Gravity SDK, LoRa operates as an autonomous, multi-agent orchestrator designed to safely retire legacy systems. It mitigates the operational risks of AI by discarding the monolithic prompt. Instead, it relies on specialized, deterministic agent workflows bound by strict enterprise constraints. By bridging local codebase analysis with global enterprise context through a strict, multi-agent pipeline, systems can be decommissioned safely and systematically. The workflow begins at the orchestrator agent. Instead of processing a massive block of text, it initializes a data packet called the decommissioning state object, or DSO. This object contains the operational state and serves as a hard constraint, guaranteeing the correct execution sequence. Handoffs between specialized workers are managed through asynchronous pub/sub delegation. The worker agents in this pipeline never communicate directly with one another. They strictly pull tasks from and publish results back to the centralized pub/sub broker. Forcing all actions through a centralized, verifiable state machine eliminates the risk of an AI generating a hallucinated or out-of-order task sequence. The broker routes the initialized DSO to the first specialized worker in the chain, the code analyzer agent. Its primary function is to inspect build manifests and configuration files to map the structural surface area of the target application. Instead of subjectively interpreting the code, this agent executes strict heuristics and regex searches across files like Maven or NPM. This produces an accurate list of all database connections and outbound API calls. It simultaneously catalogs the exposed REST endpoints offered to the network. Once complete, the agent updates the DSO state to context gathering and returns it to the broker. Local code scanning reveals exactly what endpoints exist. To determine who is actively calling them, the system requires a global enterprise view. The broker routes the updated DSO outward to the next specialized node, the context worker agent. To bridge the local agent and the live enterprise network, this node utilizes the Model Context Protocol, or MCP. Using MCP, the context worker executes dynamic, secure queries directly against the enterprise configuration management database. The agent takes the exposed REST endpoints identified during the local scan and searches the CMDB for active global consumers. This dynamic resolution maps out the hidden corporate microservices that rely on the legacy application to function. The context worker logs these live consumers directly into the DSO, ensuring they are accounted for in the shutdown plan. Fully populated with enterprise context, the DSO returns to the orchestrator. Integrating MCP provides the network-wide context necessary to ensure that no hidden consumer is left out of the final shutdown plan. In a final execution phase, the fully populated decommissioning state object is seamlessly handed off to the specialized technical writer agent. The technical writer has a singular role, compiling the accumulated local and global data into a comprehensive operational decommissioning runbook. The document follows strict templates, detailing system owners, active upstream dependencies, database archival protocols, and the exact server shutdown sequence. Once the draft is complete, the pipeline state transitions to pending review, and the entire multi-agent orchestration immediately halts. This initiates a strict human-in-the-loop safety mechanism, putting a hard boundary on the AI's operational authority. Execution remains suspended indefinitely, while an enterprise architect reviews the drafted runbook and audits the agent's internal WebSocket thought logs. No final server or routing shutdown actions can proceed with explicit human approval sent via a designated network request. This approval gate ensures that autonomous AI remains a tool to augment human authority in critical operations, never silently replacing it. Generating the runbook completes the functional objective, but enterprise governance requires an auditable record of every agent action to ensure safety. The pipeline integrates a trajectory evaluation audit, an end-to-end testing harness that verifies the multi-agent loop after the runbook is drafted. The first crucial verification checkpoint is the Zero Trust Security Audit. This checkpoint inspects the execution logs to assure architects that the worker agents did not attempt to run arbitrary shell commands during their routines. The second major checkpoint is the Worker Delegation Chain Audit. It guarantees that the execution sequence moved strictly according to the defined architecture, proving that no agent acted out of turn. Final checks assess data integrity and deliverable completeness, confirming that the code heuristics were accurate and the resulting runbook contains all mandatory sections. A standard large language model obscures its logic in a black box, making it impossible to audit. A modular, state-driven architecture produces an explicit, verifiable trail for every action. By combining precise dependency mapping with rigorous trajectory verification, LARA demonstrates how to bring automation into the enterprise, tightly bounded by zero trust oversight.